He's more than a guest, since he has been here in this institute quite some time in the past. And the little piece of paper that was given to me by the organizer says that the title is TBA, which probably in this particular case means truly brave arguments. And that's what I expect.
Truly brave what? What did you say, truly brave?
Arguments.
Arguments. Well, let me first make something a little bit clear. In 1970, whatever it was, 73, 74, I came to realize that perhaps the most important thing in the standard model, in the theory that we were looking at that time, was the Higgs sector. So as early as that time, I started thinking about the Higgs sector, and very quickly.
You can use this if you want to, on the slides.
Okay. I'm not doing anything.
Later. Okay.
And very quickly, I found these two things which actually help in understanding the Higgs, or at least making progress in it. The first thing is the cosmological constant. It is the fact, well, that was the first thing. And the second thing that I could discover at that point was the rho parameter. And these two things have to a large extent remained that way. They have been more or less the only real access things to the Higgs sector. The cosmological constant thing is very troublesome till today. At that time I was thinking, well, if the Higgs field is all in the vacuum, it's really stupid that we cannot see it. Here it is, you don't see it. So I got very annoyed with it. And luckily enough, I realized an important thing. Whatever there is in the way of matter and things, it must always interact with gravitation. So I thought, what happens when the Higgs in the vacuum starts interacting with gravitation? Well, as a matter of fact, when you put the Higgs in the vacuum, you put there a lot of mass into it, really a lot. Yeah. If you remember, just to get an idea, that if you have the ordinary quasar and things like that, you need only a few MeV to make something that becomes a black hole. Then you get the idea that if you don't need that much energy to put in the vacuum, our gravitation will do something. So I looked at that, and I discovered at that time that if there is that kind of energy in the vacuum, then the whole universe will not be bigger than a football. This is against experience. So what now? Well, there is one thing that saves you, because in the model that we have today of the universe, the size of the universe is a free parameter, the cosmological constant. So what you can do is give a preliminary value to the cosmological constant, let's say a -1, just for the idea, and then comes the theory, the Higgs field, and it compensates this one till you end up with 0. And I have compared this at times with the following situation. Suppose you have a football match, you put the ball in the middle, and they start playing, and then after you have played for 1.5 hours, you discover that the ball by accident is back at that same point within the micrometer. So understanding how you come with a prearranged constant and then renormalize it, so to say, with the theory you have, and then come out to the present situation is next to unbelievable. This, I think, many people agree, and this is what the situation is today. And the situation has become a little bit better with inflation. Inflation was some theoretical model of development of the universe after the Big Bang. And so that has improved somewhat on this cosmological constant issue. But to this day, it is a big problem. We don't know it. And there is only two questions that you can ask. The question is that a problem which has to do with gravitation, or is it a problem that has to do with the Higgs sector? Or, if I still put it differently, is it so that if you have the Higgs sector, that if it generates a cosmological constant, that you have a Higgs system which is not compatible, which is not correct? And then I should add another experience. At that time, I was very busy with doing gravitation, quantum gravitation up to one loop. And to my horror, I discovered that it is extremely difficult to do quantum gravitation in the presence of a cosmological constant. It's really just that, very difficult. Yeah. All these things like finite universes and black holes, things like that, are extremely difficult to accommodate within quantum mechanics, because you cannot relate what's inside the black hole to what's outside the black hole, etc., etc. It gets very complicated, and although there are people who do study that subject, you generally, in my taste, it's not really possible. So that's the situation, and so maybe there is something in gravitation, and so maybe we should ignore the cosmological constant thing, and maybe gravitation is not the way we think it is. That could be one solution to the problem. But, well, generally you don't know. And so I have taken a little bit the other direction. I have now taken the direction that the Higgs as such doesn't exist. That means there is no vacuum expectation value. That means there is no cosmological constant. So that's the situation that we are, and which I want to explore. I want to explore the situation that there is no cosmological constant. And then you get this. So far, I'm now speaking before the CERN discovery of last week, or this week, what is it? I don't think we should take that too seriously right now. And then you know that the Higgs, there has a limit of about 114 GeV, which is the region that could have been explored by LEP, the previous machine at CERN. If it was 114 GeV or less, we would have seen it. It's not there. And here I have to tell you a little psychological fact. You see, there in 75, I look at the Higgs and I say, you know, this thing is too crazy to exist. At that time, people didn't know about the mass of the Higgs, and it could be as low as something like the Kaon mass. So in 1975, say, the limit on the Higgs was half a GeV. And then there came series of all these crackpots that you can find so many in our theory department. You got all these theories that people proposed for the Higgs. And as time went on, one after the other would predict the Higgs, and they would get there, and it was no more theory. So this has been going on. So to me, personally, from the point of view there is no Higgs, the past, let's say, 25 or 35 years, I have seen all the other guys falling away, all the other theories with a finite Higgs mass, and in the end we come here. You have to understand that's a strong psychological argument for thinking that you are right. Yeah? I'm almost the only survivor of hypothesis of the Higgs. Yeah. You should not underestimate that. Okay, so that is the situation that we have today, and we cannot, after that you realize that if you cannot see the Higgs directly, there's only one other thing you can do. You can look to the radiative corrections that are generated by the Higgs. And here you meet another problem. And the problem is that standard radiative corrections become smaller as the particle who takes a part in those corrections becomes heavier. For example, if you speak to the radiative corrections of the electron anomalous magnetic moment, you don't have to include any other particle except the electron itself. because the others are too heavy. You don't even have to include the muon, which is only 100 MeV. So radiative corrections tend to become smaller as the particles associated with it become heavier. Now, a great exception to this rule, which you have to look for, is the rho parameter. The rho parameter is something which is what it is because of the symmetry in the theory, and because what happens is that if you have a very heavy particle that breaks the symmetry, it reflects itself in the correction to the rho parameter. So the mechanism whereby the rho parameter gets a radiative corrections is very drastically different from any other radiative correction. Yeah. And you have it here. The rho parameter is defined, maybe I should say something about that too, as the ratio of the charge to the neutral vector boson mass corrected by a factor cos theta. If you have the most simple Higgs system, which happened by accident to be the one that Mr. Weinberg was using at the time, then that's equal to 1 plus radiative corrections. Radiative corrections being things, quantum corrections that arise if you make a calculation of one loop or more. So this is the rho parameter, and the wonderful thing about the rho parameter is that, well, I'll show you on the next slide. The rho parameter here becomes equal to a correction that is related to the top quark, because the wonderful thing is that as particles get heavier, they contribute more strongly to the radiative correction of the rho parameter. So by the way, you discover from this also that you should not start thinking that there is a forced generation or something like that, because we have observed the rho parameter, and it is as it is. It is as tight as it can be. You cannot have another contribution there due to a heavy quark. So this radiative correction is a very wonderful one, because it gives you a look on the spectrum all the way to the stars, so to say. Yeah. And the first correction is due to the top quark, the top and the bottom quark, and the top quark is so heavy, and it is due to that it contributes a lot to the rho parameter. And in the historical development of physics here, it has been this measurement of the rho parameter has provided the experimentalists with an estimate of the top quark mass, and indeed that's where they found it. That's the funny thing. Us theorists have been proposing mass values for almost every particle they were looking at, like the W's and so on, and the Z. And now there's one for a top quark, and that was predicted to, or at least related to another measurement. And, well, I think that is in some not so small sense a good thing for the theory. Now, the top quark mass was found, and once you have the top quark mass, that thing called C top can be calculated. And then there's another correction, and that is the one which depends on the Higgs mass. And if the Higgs becomes heavier, again, this correction becomes bigger. So there you see the correction, and you see one thing. It is small. There's a small coefficient, 8/10,000, something like that. Yeah? So when I remember writing down, discovering this term, computing it, I thought there's no way that the experimentalists can ever get that precision in the measurement of the masses of the vector bosons and the weak mixing angle. But they did at lab. They actually did it. They did measure something which was not to the percent, but on the tenth or 100% of a level. And that's how at the experiments at lab, they have been able to determine the rho parameter to great precision, which allowed them to make an estimate of the Higgs mass. And I can present that in the curve, the well-known curve. This is a curve that the horizontal scale is the Higgs mass, and the curve that you see is the probability that that given particular Higgs mass is possible. So for instance, if you a Higgs mass of here like 30 GeV is excluded with 6 standard deviation, 6 sigma. So this is the curve of probability of existence of the Higgs. Now in actual fact we know already about the Higgs something. We know that yellow part there, that's the part that is excluded because of the lab experiments, and it gives you that area where the lab people would actually have seen that Higgs. So that's the 214 GeV. And then from the other side, there are things, other experiments, the tevatron, etc. You can see that thing here, and you can see also that it is excluded by virtue of the fact that it gives too big a correction to the rho parameter, bigger than has been seen. So in the end, all we know, what we know till about last week, I suppose. Wonderful that I can use that. Hey. Still hey. So this area that you see here is the one that is allowed still for the Higgs with a certain amount of deviation, because you see you have to go at least to 1 standard deviation to start accommodating it with this thing here. Now the Higgs that they have found at CERN figures around 120 MeV, that's here, 120, something like that. And so you can see that's as close as possible as it could be. It is sort of in agreement with some events found at lab at the last, at the bitter end. So maybe that's the true thing, or maybe it's not. I really have no idea. In any case, this is the situation. And then when I look at this situation, I get uncomfortable. It looks that in the end, maybe I was right and there is no Higgs. When if you hadn't listened to CERN this week, you would be convinced, or at least feel compelled to think in that direction. Yeah. Okay. Now there is an interesting fact, and that has to do with the radiative corrections to the rho parameter. If I have repeated that formula over there. The rho parameter has a known correction, which is due to the top quark mass, and then it has that other reaction, the correction, which goes as the log of the Higgs mass. Now you notice that contribution there goes to 0 if the Higgs mass is equal to the vector boson mass. Yeah. That is to say, the case that the Higgs mass equals the vector boson mass and the case that there is no Higgs at all, I cannot distinguish from this previous curve. They are the same result. So I come to the conclusion that the case of no Higgs at all is here. That's the most probable case, so just in the bottom of that curve. So that sounds like encouraging for the idea. Here it is. This is the plot of having no Higgs, and you can see it fits excellently with the data. But, as it is always with those things, there is, how you call it, a fly in the ointment. Yeah? That's the American expression. In Holland we say there's a fly in the porridge. The difficulty is this. If you assume no Higgs, you have to ask yourself, how can I understand the situation of there being no Higgs? And the difficulty, number one, is that this rho parameter I'm talking about here, I would have a hard time understanding that this thing is 1 plus radiative corrections. So that's difficulty number one. Now you can start doing something about that and start studying the situation without the Higgs. And at once you understand that you have a multiple capability here depending on the Higgs sector. You see, if you start with the simplest Higgs sector of the standard model, and there's a certain Higgs mass, and now I start to understand the situation of no Higgs which amounts to me, that's what I always try, make the Higgs mass go to infinity. The idea being that once you cannot make it ever, that's the same as not having it. Now, if I do that with a standard model, my rho parameter will neatly stay equal to 1. Yeah. But if I start from a Higgs sector which is different, then my rho parameter will not be 1 when I take the Higgs masses to infinity, and I get another situation. So, in other words, the limit of heavy Higgs, the limit of there being no Higgs, is ambiguous. There's more than one way to get there. So that's another problem. So this whole thing is not that easy. Anyway, now, as I say, the heavy Higgs limit is not unique, and if we take any other Higgs sector than the Higgs system of the standard model, then the rho parameter can be anything you want. So the situation gets more complex. There's nothing we can do about it. It has been studied in the published literature, and in the published literature, we usually have stuck to the Higgs of the standard model, since after all the rho parameter is equal to 1, so you steal this idea from the experiment. Now, so that comes the next thing, is the heavy Higgs. Now I have to start studying the theory without the Higgs. And how do I do that? I do that by taking the standard model and I let the Higgs mass go to infinity. That's the idea. It's not an easy thing to do, but that's what you try. Yeah? So the question is, what happens? Yeah. And the radiative corrections due to the Higgs become large. Yeah? And in fact, so large that perturbation theory starts breaking down. So the first thing you discover is that your beautiful, and of course that should be, a renormalizable theory is a theory which by definition goes like a perturbation theory. We know that we need a Higgs to have the theory renormalizable. That means that if we don't have a Higgs, the theory has a sector which is non-perturbative. That's quite possible, there's nothing wrong with it, but that's what you have. And it also means that you cannot compute things. Now the Higgs sector in the limit of a heavy Higgs looks, and that's the other accident, there is an accident that happens, and it is when you look to the Higgs sector, then it starts to look, and you make this limit, and it starts to look like the sigma model. The sigma model is an old model that looks exactly like the sigma model. The sigma model in the old days was used for describing the pion system, scattering of pions. That was the sigma model, was described by Mr. Schwinger. And it was called the sigma model because there's another particle in it, the sigma. And if you got from the sigma model to in the limit of infinite mass of the sigma particle, what you got is known as the nonlinear sigma model. So it looked that to study this affair here for the heavy Higgs, you had to go to the nonlinear sigma model. And there exists work on that and literature. There was work by Mr. Harry Lehmann, I remember, and that was the study of that system. And I tell you the very special thing that Mr. Lehmann and others did. They did pion physics, and we have all noted, we note that in the pion system, such as we see experimentally, the pions show a resonance at about 750 MeV, which the rho meson. And I'm sure that many of you know about the rho meson being a 2-pion resonance. Now the question is, what does that happen in the case of the vector bosons? When I take that sigma model and I apply that knowledge as well. Well, the fact there was this previous work of Harry Lehmann on that issue, and he tried to understand how pion plus pion can give a resonance, the rho resonance, and discovery number 1 of Mr. Lehmann was that within the sigma model itself, you cannot have it. It will not be there. And this is it time or something?
You have 7 more minutes.
Thanks. And so that's the situation that you have, and that is that the rho meson cannot be understood if you just look to the sigma model. The solution that was discovered by Harry Lehmann is that he discovered the coupling of the pions to the nucleons, and then it turned out that a closed loop of nucleons did actually produce the rho meson. Now this is very intriguing. So if you take this reasoning over to the standard model, and if we were to have a resonance which would manifest itself as a resonance between NW-W scattering, if there would be such a resonance, it would imply that you get something that could play the role of a nucleons. And this is of course a well-known thing, that's Technicolor or something like it. And it is, that's what you would need. But it could also be that there is no such peak, no rho meson, and then you are in trouble because there will be no resonance and you don't know where to go. Now, all that was spelled out in the investigations here. Another thing that you can have is an invisible Higgs. I have not speculated on that, but Mr. van der Bij in Freiburg has speculated on the invisible Higgs. There is something called the U particle that was introduced to make a funny model that you have that has two parts. Here's a standard model, here's another standard model. They connect it by something called the U particle, and you make that sufficiently heavy and you have no leaks of one to the other. So this is one model that you can have, and the U particle you can then couple only to the Higgs of either side. But that's one model of making it, and it's sort of an interesting model for all kinds of reasons. One of the reasons is, you know, you have to understand in that system you have two standard models, and here's the one that we are made of. That's our electron, our proton, what have you. Here you have another one, and somebody else is made of it. But you see, they don't interact. So maybe at this moment, if this were true, there's another Veltman going by here, speaking to another audience, and we are not aware of it. That could be. So it's of course obvious that this would be an ideal candidate for dark matter. And astrophysicists, as you know, are always people who are ready to believe whatever presents itself, would be very happy with this excuse. Yeah. So, but this model somehow associates with itself an invisible Higgs. It would be, for those who want to look to the present data, if you have a model like this, one of the things that you can have is that the photons they see at CERN, the two photon events they see, if they are not peaking at a very definite mass, it would be this kind of model you get to. Well, not precisely this one, there are variants of this. But you have to understand that the CERN people, instead of discovering the Higgs, could have discovered a spectrum of Higgs-like stuff. Yeah. And in fact, it seems that one of the groups finds that their events are sort of spread all around the place. So whether this is true or not, I really don't know. Well, if no Higgs is seen in the near future, yeah, then there is no Higgs, or the Higgs is less visible. Yeah. At this time, the no Higgs possibility seems preferable. That's what I think, because of the excellent fit to the rho parameter. You know, dot there in the middle. So it would be one thing. Yeah. However, the above two options, invisible or not existing, are more or less are not really the same thing. And to find out about the one or the other, if you have this situation, then experimentally we have to go to W-W scattering. And this is one of the things that come with the territory. If you have a situation like this, you will have to start observing at the LHC the scattering of vector bosons on vector bosons at bloody high energies. You know, I'm now really talking about, I don't know, 2 TeV or something. Yeah. So I don't know if we will ever see this or if it ever will be done, but life will get very, very tough. Yeah. So it seems that the LHC should be used to explore also W pair production as precisely as possible. Or if that cannot do it, then we have to wait for the next linear collider. And I don't see that coming, actually. Thank you very much.
questions? Yes, right here. Our elegant boss is going to ask a question.
In this fascinating alternative for dark matter, where you have another standard model, presumably the relic density of that dark matter will be the same.
Well, you don't really know it. If it is the same standard model, yeah, it would look the same. Yeah.
But data say that
they would
there
have
are more dark matter than ordinary matter. Maybe you can have a collection of standard models, 5 or 6 standard models.
Well, there's room for it.
The number has been measured. It's the ratio of dark matter to ordinary matter. So it's about
Dark energy.
5 or 10.
7.
7. Any other questions? Surely there must be some other questions.
I've beaten them. Oh, not completely.
Yesterday during the dinner we were talking about the cosmological constant problem, as you mentioned today, and about the chiral symmetry breaking, no? Because there also you have a cosmological constant. So what is your opinion about that?
What did he ask?
Chiral symmetry breaking.
Oh yeah, that also gives rise to a cosmological constant. Mm-hmm. Yeah, absolutely. Much smaller though, but it gives rise to that too. So you have the same problem there, and usually people just walk over it, but I really don't know why. It is a problem. It simply is a problem.
Mm-hmm. Vacuum oscillations, if you don't do normal ordering, which is arbitrary, that's an infinite one, so much better.
If you want to look for more difficulties, there are lots of them. Thank you, Alfred.
You're welcome. Thank you, Peter. Any other questions? Yes, there's one up there.
Next to Cecilia.
Just one comment, which is more or less in agreement with your comments also. I don't think there is nothing in contradiction with the fact that they are somehow looking now, and it seems to be a sort of a Higgs there at the light value, say 126 or something like that. And apart from that, there could be a strongly interacting WW scattering at high energies. I don't think there is a contradiction with that. There could perfectly happen that they find something that resembles the Higgs, maybe it's a composite thing, or who knows, something that looks like a Higgs, but there could also happen at the same time that they find a strongly interacting WW scattering. I don't think there is nothing in contradiction with that. I just wanted to mention that. What do you think about this?
What was she saying?
She's saying that everything might be true simultaneously. A rho-like WW resonance and a Higgs.
What do you think, Tini? I mean, could it happen that there is something that resembles a scalar particle, maybe this U particle or whatever, what they are finding now at the LHC? And apart from that, they could also find resonances in the WW scattering. Why not?
Well, it could.
No, I mean, there is nothing against that, really.
No, I mean, you can endlessly complicate the standard model. Yeah, and this was only one of the ways of doing it. Mm-hmm. And it was a way which had certain advantages with maltreating the Higgs sector, so to say. Yeah. And so that's all I can say about that, but by itself you can have all kinds of things. Mm-hmm. But you have to understand, I find finding a Higgs at this point would to me be a disappointing experience. And the reason is that you sort of close the only door that you would have at something that doesn't check. Yeah. So, and since there are so many things about the standard model that we do not understand, like the masses of the particles, like why there are 3 generations and so on and so forth, I'm not very happy with a situation where the experiments close in on something which is entirely understood and which has no open door and no escape possibility and nothing. You know, it's really a horrible situation. You don't know where to start looking. At least now we know where we have to start looking. That's at the Higgs sector. And you have some hope that you can find something there because the thing seems to be intimately related to gravitation and the masses and what have you. So if there is some funny stuff going on, that's the place where you want it to be. Now, if they find it as advertised, that door gets bomb in your face. You understand what I'm saying? And this is the idea. I want to have a clue. Where can I? What can I do? I have the feeling you don't agree with that, David. No, he doesn't.
I have a question related to David's disagreement. How much more disappointed would you be if they found supersymmetry?
But you see, the supersymmetry is another story. By itself, I may point out to you that I have been one of the first to start actually advertising supersymmetry. Now that may come as a surprise to you, but if you look to my Fermilab talk of 1979, you will see that that's actually happening. Yeah. But the thing doesn't materialize. Yeah. So, to me, a successful theory is really something like the Standard Model was. In 1971 there was nothing, then there came the Standard Model, and then for a little while there was nothing, and then everything started to fall together. That's how a good theory should work. That didn't happen with supersymmetry. It didn't happen with string theory either. They are isolated experiences. They're sitting in their own institute, and in this institute, maybe in some corner of the institute. Yeah. You want to say something about that?
I will have a chance. Huh? David has an entire half an hour to answer.
Well, try to get away with it, yeah? Okay.
So let's thank the speaker once again.